Hey, hello everyone. Today we're going to be looking at Chapter 9, Conics or conic sections. And basically what we're going to be looking at with these is two kind of double-naped cones stacked on top of each other and the intersection of a plane with that particular figure. If we look here at the first one, with the intersection of that plane, if it is horizontal, then we're looking at the intersection between the two objects being a circle. If that intersection is a bit more skewed and less horizontal, it gets a little bit more like an ellipse. And then if we intersect it down here more with just one edge, we start seeing a parabolic shape for their intersection. And then lastly, if we intersect it more vertically, we're looking at hyperbola. So these are the four basic conic sections, or just conics for short. Now there's a couple other types of intersections, and these intersections happen when we kind of ignore the rules that we're not going to go through this center point where the two cones touch. And if we do that, we just get a single point. If we go directly down their edges diagonally, we get a straight line. Or if we go directly in the other direction, we could get two intersecting lines. So these are what are called degenerate conics, and we're really not going to focus on those at all, but it's good to mention them. The first type of conic that we're going to actually look at is the first example there, which was a circle. And most of you already know, or you should know, the equation for finding a circle, the standard form for that. And just as a reminder, it's going to be x minus h squared plus y minus k squared, and that is going to equal r squared, where hk is your center point, which is said right here, and r being the radius. Okay, so here we have radius, center point, and xy is just the collection of all points that are so far this radius away from the center point. And that's how we create the circle. So there's a couple different operations or things that we're going to be doing with them. Very basic things. So let's just start with the first example, which is saying I have a specific point and I have a specific center point. Give me the equation. Okay? Some of you might be able to jump right into this, but let's just do it to make sure everyone's on the same page. First of all, we need radius. If I look back at my equation, I need x minus h squared plus y minus k squared equals r squared. So I need radius and I need center point. I've been given center point, and I've been given one xy value. Luckily, that's enough information for me to get the radius, and some people might be a step ahead of me here, saying, well, the radius is just going to be the distance from the center point to any point on the circle. So the fact that they've given me a point, in turn kind of gives me the radius if I just use distance formula. So what I'm going to do here is say that my radius is going to be equal to this big long square root 1 minus negative 2, and that's all squared, plus 4 minus negative 3, that too is all squared. Now what I've done here is taken the first x value, subtracted it from the second x value, and then taken the first y value, 4, subtracted it from the second y value, 3. So now this will be giving me the distance from the point to the center. So 1 minus negative 2 squared, that's going to get me 3 squared, which is going to be 9. And over here, this is going to be getting me 7 squared, which would be 49. Adding those two things together, giving one of the square root. And I'm getting the square root of 58. Fantastic. That is my nice, clean number for my radius. Now all I need to do is put it all together in the equation. And the equation tells me that r squared equals something, something, something. So r squared is just going to be 58. And that's going to equal x minus h. Well, h technically is a negative 2. So x minus negative 2 gets me plus 2 squared plus y minus k. K is technically negative 3. So that's going to be plus 3 squared. And that is my equation. All right. Do me a favor and try exercise 9. This is section 9.1. So do exercise 9, and then we can move on to the next example. Okay, once you've done exercise 9, we're on to example 2, which is going to be sketching a specific circle. So we're given all the information that we need. We just actually want to draw the thing by hand. And the issue with this, though, is the information is here. It's just not given in a way where I can very easily, pull out what is the center, what is the radius. So we're going to go ahead and put it into that kind of form. And that form again, x minus h squared plus y minus k squared equals r squared. All right. So x squared minus 6x plus y squared minus 2y. I'm just rewriting, and actually I'm going to move the 6 over to the other side just to get us started. Now, why did I do that? Well, because now, if I'm going to draw some parentheses here, I have kind of two different pieces. I have my first piece, which deals with the x's, second piece, which deals with the y's. And they're kind of these two binomials that are just waiting to have their square completed. And why does that even matter to me? Well, because I want them to end up like this. I want to be able to factor them down in that way. And the only way I'm going to be able to do that is if they're perfect square trinomials. So I want to complete the square on both of these two things, and then that'll make my my standard form much more apparent. So I'm going to go ahead and complete the square. On the first one, first, I take the 6, cut it in half, square it. So that gets me plus 9 on both sides. And then I'm going to complete the square over here. Take the 2, cut it in half, square it, and that gives me plus 1 on both sides. So now let's rewrite this whole thing with the squares completed. X squared minus 6x plus 9. That's my first perfect square trinomial I've made. And then y squared minus 2y plus 1. That's my second perfect square trinomial I made. And then the combination of the negative 6, the positive 9, and the 1 gets me a 4. Okay, so now I can factor this down nice and easy. And this will become x minus 3 squared. Over here, y minus 1 squared. And this is technically r squared over here. So this is 2 squared. All right, now we have all of the information that we would need in order to sketch. Right, I have an h and a k. The original format says x minus h. So this h value is positive. So hk equals 3, and again, y minus k. So this k value is positive, 1. That's my center point. And my radius equals 2. So when going about graphing this thing, you can immediately plot the center point, and you can draw a radius, but it doesn't really give you all the points of the circle, very, very clearly. You have to draw the center point, which would be right here, and then kind of, trace out. From here, 1, 2, that's the radius, that brings you to 5, 1. You can trace up, 1, 2, and that brings you to the top of the circle, to the left or down. But it doesn't need to be, too crazy of a process. You know, plot the center point, move out the radius in a bunch of different directions, and you have your circle. What I would like right now is for everyone to try exercise 29 and try and graph your own. After you've done that, we can move on to the next thing, which I believe we're moving into talking about parabolas. All right, so once you've done exercise 29, we're moving on to parabolas, but we're doing parabolas in a way that might, gain a little bit of confusion, because all of you know what parabolas are. You've worked with parabolas before, but we're going to be looking at them in a more of a geometric sense in terms of conic sections. So it's not going to be, just as simple as a quadratic equation, right? So we have to, kind of take that idea and push it out of our minds and take in some new information. A parabola is essentially almost like half of an ellipse, if you want to think of it in that way. So it does have some of the same ideas, like a focus point, and we're going to go ahead and use things like that in order to make the equations for them. So there's a little bit of vocabulary that we're going to be using that I want everyone to be familiar with. First is directrix, which is essentially this invisible line that always comes on the outside of the parabola, which is equidistant from the vertex to the focus. All right, I think we've all heard the term focus point when talking about ellipses, and it's the same idea. And this directrix line, again, is equidistant from the vertex as the focus is from the vertex. And we would define a parabola in this setting as a set of points that goes equidistant from both the directrix and the focus. So wherever this line travels, it will always be the same distance from here as it is from this line down here. Alrighty? So I know it's a little bit different, and this page is most likely going to make everybody scream and cry. But I'd like, just to ignore all this stuff up here. Don't worry about this stuff. We'll get to it later. I want to just look at right down here. Right here is what we're looking at for an equation that's at the origin. So something like y equals x squared. That would be defined as this type of equation right here. Now, we have two different ways of defining them. One where we're looking at it being vertical, and one where we're looking at it being horizontal. So we can have parabolas that are going this way, or we can have parabolas that are going this way. Now, that's why I said that this one is more like y equals x squared. But the thing that's kind of weird in here is, if I manipulate this thing and get y by itself, it says y equals x squared, yes, but over 4p. So the thing that's weird and kind of added to this thing is this divided by 4p. And all that this new variable in there is an idea or a piece of information that shows us how far from the focus the vertex is. So, it'll explain to us how steep or how flat the parabola is based upon the p-value. So in this case, if I was just looking for y equals x squared, that p-value would have to equal 1/4, meaning that the focus will be 1/4 units away from the vertex. So that would make the equation y equals x squared over 4p, or 4 times a fourth, which would just be 1, which translates to y equals x squared. Okay, so when we look at that original parabola that we all know, that parent function y equals x squared, we know that the focus of that parabola is 1/4 units away. Okay, so we're kind of just adding a new piece of information into the equation. And the same is going to be true for these equations up here. These more just talk about parabolas that aren't centered at the origin, so they get a little bit more complex. But that's what we're looking at down here. Let's look at an example and try and just work our way through it. The first thing that we're going to do is find the standard equation of a parabola which is at the origin, which has a focus of 0, 4. All right, so if I am correct, I won't be giving away the answer by showing the graph. Well, I do, but it's fine. So the focus is 0, 4, and we know that the parabola is centered at the origin. Ignore this for now. That was the answer. So the standard form, like we just saw on the other on the other page, was x squared equals 4p times y, right? So we need p, essentially. Everything else is taken care of. X and y is not a big deal. So p stands for the distance from the vertex to the focus, which kind of is, given. It's not that hard to find there. It's from 0, 0 to 0, 4, which means that p just equals 4. Okay, this seems like it's too good to be true. 4, and then p is 4, and then y. So x squared, you're telling me, is just going to be 16y? Yeah, exactly. And now if I wanted to get y by itself, to get it into a more familiar type of equation, y would equal x squared over 16, or y equals 1 over 16 times x squared. And this would be the more familiar way of looking at it, but right here would be the way that we would define this equation. Okay, so not too bad. I would like everyone to try to do exercise 51. And then once you're done with that, we can move on to our next example, which will be using one of those forms where they're not centered at the origin, which gets a little bit more complex, but I want to make sure you're good with this first. All right, the next equation is going to be, like I said before, talking about one that's not centered at the origin, which means we need to look at our format for the standard form not centered at the origin, which is kind of reminiscent of like a circle or the ellipse type equations. We have x minus h squared, and that's going to equal 4p y minus k. So it looks very much like the ones that are centered at the origin, which say x squared equals 4p times y. So the only difference here is that we're adding in minus h to here, we're adding in minus k to here. So basically it's saying, if these were zeros, yeah, this is it centered at the origin, but these two things are not going to be 0 because the vertex is changing, so they are going to be shifting the graph in a specific way. So again, much like we did with the circle, we need to take this equation, manipulate it a little bit to make it look like it's in this form in order to pull out all of that good relevant information. Okay, so first thing, I want y's and x's on different sides of the equation. So why don't I go ahead and, I don't like the fact that there's 1/2 here. I'm going to go ahead and change that first off. Multiply both sides by -2. Now over here I'm going to get -2y equals, I multiply by -2 so I can get just a positive x squared here. And I can get a plus 2x, I can get a minus 1. All right, so now it looks like I'm in a good spot right here if I could just factor this down. Unfortunately, this isn't in the spot right here where it factors down into a perfect square, which again is the type of factoring that I want to look for. So I'm going to get rid of that 1. I'm going to bring it onto the other side. So I'm going to add 1 to both sides. That's 1 minus 2y, and that's going to equal x squared plus 2x. And that frees me up to have this open space here where I can complete the square. And completing the square gets me plus 1 on both sides. Cool. So now I'm going to go ahead and simplify a little bit. That's going to be 2 minus 2y. And that's going to be my perfect square trinomial over here, which I'm just going to go ahead and factor it down right now. X plus 1 squared. Awesome. So now it looks like I have this side of the equation. So the other side is really missing some sort of distribution, because I have y and I have a number, but I don't really have anything on the outside, unless I'm considering it to be a 1. But there is more. I can pull out a common factor over here. So what I'm going to do is take out negative 2. That's what it looks like I can do, because I want positive y on the inside of that parentheses there, and right now I have negative y's. I'm going to pull out negative 2, and that's going to get me a positive y, and it's going to change this 2 to a negative 1, and that's going to equal x plus 1 squared. So now I have it all set up perfectly in my format, and you'll notice all of the choices that I made going through this whole process have been just to kind of appease this formula over here. You know, I wanted to make this a perfect square trinomial so it could get into this kind of factoring. I wanted to pull out negative 2 over here because I needed a positive y inside of here. So just keep in mind where you want to end up, and you know the moves will kind of come along with it. So what's the focus of the parabola? I guess that's what we were doing this whole time anyway. So the focus is given by which part of the equation? Well, I need to find the vertex, and then I can trace up, so many p values to the focus. So I need what is p, and what is the center point hk. Well, it says x minus h and y minus k. So x minus h would be negative 1, and y minus k would be 1. So negative 1, 1 should be my center point, and p comes from over here. Right, so 4p should equal negative 2. If I were to divide by 4 on both sides, p should equal negative 1/2, which means that if I go from my center point p units, I should get to the focus, which tells me that my focus should be negative 1, 1/2. Now, why did I only change the y value? Well, this is an equation of a parabola that's going in this direction. My vertex was here. My focus is going to be here. So what I need to do is only go and change the vertical direction, because the horizontal direction isn't coming into play when I'm looking at where the focus is. If I realize that I have a parabola going this way, and I have the vertex, and I know the focus is so many units away, then I'm only changing the horizontal. So you need to realize which way your parabola is moving in order to know which part of the equation to change. So our focus was at negative 1, 1/2. Now I would like everyone to try exercise 6-9. When you're all set with that, we have one more example to do, which is finding the tangent of a specific, at a specific point, the tangent line at a specific point. Alrighty, so when you are finished with exercise 69, we are going to be finding what's called the tangent line, which is at a specific point on a graph. You see how the slope of a parabola is constantly changing. We can kind of isolate that at a specific point and say, what is the slope, what is the equation of a line at that particular point? And this thing is going to be moving in a straight line. It's a vertical, sorry, not vertical, it's a linear equation at that specific point, which isn't going to follow the quadratic the entire way, but it's the slope at that particular point. So the question is, how do we go about doing that? And now, I am not going to go through this entire example with you, but I am going to give you some key information. I will give you the fact that there are specific distances from the focus to whatever point we're looking for the tangent line, as well as from the focus to whatever the y-intercept of that tangent line is. And that distance 1 and distance 2 are equal. Why is that true? Because what happens here is we are making an isosceles triangle. You notice these two symbols right here are indicating that these two angles are the same. So with this being an isosceles triangle, these two lengths will be the same thing, and that will be crucial to trying to find out what the equation of this tangent line right here is. Another piece of crucial information I will give you is that the tangent line is linear, which implies that you need the slope and the y-intercept. So this 0b is not going to cut it. We need to figure out what b is, and then be able to use that to have 2 points and find the slope. So your first step should be finding b. Second step, get the equation. All right, I want everyone to try this one, do your absolute best with it, and then when we come into class, we'll take a look at it, and we'll do a couple of others. Good luck.